Thank you very much, Dimitri. So we'll start the tutorial session by Andrew Tolley from Imperial College. I will be talking about effective field theory approaches to gravity. I'd just like to say that, as Dimitri mentioned, there'll be room for 10 minutes questions after his talk, but then there'll be a much longer discussion period tomorrow at 2:30 p.m. That's Florence time, whatever your time is. And I also like to encourage everyone who is not asking a question right now to mute themselves so as to avoid any echoes. Thank you.
Can you see my slides?
Yes.
Yes.
Okay, great. Shall I go ahead?
Yes, maybe just remember if it's possible to have maybe a 5 minutes break in the middle, more or less, of your lecture, whenever you want.
Okay, so thanks a lot. So this, what I'm going to talk today is about effective field theory approaches to gravity. This, and just so there's no confusion, what I really mean is about viewing gravity itself as an effective theory, theories of gravity. And so really this is going to be discussion about extensions to gravity and how we go beyond general relativity, how we think about modifications to it in the language of effective field theory, which is the language we should think about things. So just to start off with, let me remind you what an effective field theory is. And this is sort of a formal path integral way, but I think it's nice. Whilst it is cartoonish, it gets across very clearly what's going on. So the notion when we talk about an effective field theory, the idea is that deep down there is some fundamental theory, which nowadays we tend to call the UV theory. So the whatever it might be, maybe it's string theory or some other, Higgs theory and unified theory, whatever it is. And the fields within that theory naturally can be split into some fields whose masses are below some scale and masses are above some scale. So I just referred to those as the light fields and the heavy fields. Now, of course, there's many ways to do that. And so, in fact, there's many different types of effective field theory, even from the same UV complete theory, depending on what we choose to classify as light and what we choose to classify as heavy. And the low energy effective theory, we should think of as what we get when we do the path integral over all the heavy fields. So we integrate them out and we ask, what effective action would we need in order to write down such that then if I want to compute, say, light field correlation functions or light field S matrices or basically any physical observable coming from the theory built out of the light fields only, what effective action would I need to use? And in principle, we just need to calculate that by doing the path integral. Most of the time, we work in the opposite direction, which is where we work from the bottom up, where we just try to guess the form of what that light field effective theory is by writing down every local operator we can, built out of the fields, the bosons and the fermions, normalized, respecting the symmetries of the theory, the global and local symmetries that we would expect, so that it'll be fields, derivatives of fields that may need to be covariant depending on the symmetries, etc., etc. And I'll give some examples of that later. But just to say, if you do know what the UV theory is, then there are basically two types of contributions you get when you integrate out the heavy physics. The stuff, the tree level stuff, which is what you would get if you just took the UV theory and you solved the classical equations of motion for the heavy fields, whose solution, let me denote it as h of light. So a heavy field is a function of the light fields by virtue of its classical equations of motion. Substitute back in, and that gives basically the tree level contributions to the low energy effective theory. And so in certain cases, those are the dominant contributions. For example, when we talk about string theory, the alpha prime corrections in string theory, they're exactly those tree level corrections that come from the massive spin states on the string, but it's all tree level. It's not loop corrections. It's distinguished from the G string corrections in that sense. But in addition, of course, we have the loop corrections. So how would we compute those in practice? we'd split the heavy fields up into, expand it around the solution of the classical equations of motion for the heavy fields in terms of the light plus some fluctuations, perform the path integral of the fluctuations, and usually we do this in some context of a loop expansion, so the one loop term would, for example, look something like that. So when you do that in general, in effective field theory, what you get is an infinite number of operators, but that are suppressed as they become more irrelevant. So as their effective engineering dimension becomes higher and higher, they're more suppressed by the scale lambda, which is we call the cutoff scale of effective theory, but it's really, in this example, the way I've described it, it's the scale that distinguishes what's light and what's heavy. So we separated out those degrees of freedom whose masses are less than lambda and those above masses above lambda. If we integrate out the heavy ones, then we'll generate an infinite number of operators in the low energy effective theory, most of which are irrelevant. So we don't get renormalizable theories from this. So effective field theory is the sort of just natural description for theories that aren't renormalizable when we have to live with the fact that we have these irrelevant operators. But nowadays, of course, we don't worry about that. For example, if you truncate the effective theory, you'll get high derivatives, even already in the quadratic part of the action. Say for some scalar field, you'll get higher derivatives there. If you truncate that, you may worry about additional states, ghostly states that arise because in the effective propagator, you'll have additional poles from the truncated effective action. But you shouldn't take any of those seriously because the mass of all those states is exactly at the cutoff, which is precisely at the point at which I don't trust the effective field theory expansion anymore. I should only trust the effective theory at energy scales well below that scale, which I've integrated out. And so that's why we don't worry, for example, about higher derivative operators in an effective field theory, because the additional degrees of freedom that they appear to represent are not actually there. They're not physical. They don't have asymptotic states. They don't contribute in anything important. Another trick that we do a lot, and I'll use this later in some examples, is to make copious use of field redefinitions. So when we construct a low energy effective theory, we often change our definition of fields for convenience purposes. An operator that can just be removed, set to zero by virtue of a field redefinition is called a redundant operator. Now, often we do this purely for practical reasons, but there's a well-known theorem that the S matrix is invariant under local invertible field redefinitions. And so if you're computing scattering amplitudes, this is always a legitimate thing to do. The crucial thing is that they have to be local and they have to not change the definition of asymptotic state. So here's a simple example where I could redefine the field by something nonlinear with higher derivatives and so on. But locally, order by order in expansion 1 over lambda, it's invertible. I can go between those two definitions of those light fields, and therefore it's acceptable. It won't change the S matrix, but it does change correlation functions. And so you have to be wary of that when you're doing it and what the significance of that is. So essentially, there's two types of modifications to gravity, which we'll understand. So let's now think about gravity itself. There's two types of modifications we tend to have in mind. There's those that are really UV modifications, where we imagine new physics at some very high energy scale. So the obvious things are the Planck scale, the string scale, some grand unified theory scale, et cetera, but some scale which is higher than the scales that we've currently probed. And then there's also IR modifications, which have been significantly considered in the cosmology community for reasons I'll get to later. So just first off, let me think about UV modifications. This is to some extent better understood, more well established. So string theory, for example, is an example UV modification of general relativity. String theory gives rise to a theory looking like general relativity, specifically a supergravity theory at low energies, but at high energies it looks very different. So it is specifically a modification. And as already mentioned, the so-called alpha prime corrections, which are just tree level effects in string theory, already encode modifications that depart from general relativity. So it only looks like it at low energies. But it's well understood how to account for all different modifications from UV physics in the low-energy effective theory at low energies by utilizing the language of low-energy effective theory. So the cutoff scale may, for example, be the string scale or the Planck scale. So indeed, even if you're just looking at pure gravity and you forget about matter, you don't think about anything else, no fermions, no scalars, etc., just pure general relativity. When you regard it, the modern way to regard general relativity is not the end of the story, but really as only the leading term in effective field theory expansion. I should say general relativity and cosmological constant, but that piece is always a given, so I'll just drop that piece. And so if we follow the logic we had earlier, the effective field theory, the bottom-up logic, then what we're supposed to do, if we want to write down effective theories, we write down every local operator that we can write down, appropriately suppressed by the cutoff scale lambda, whatever the scale we anticipate the new physics to come out in, and provided the operators we write down respect the symmetries of the system. So for general relativity, the symmetry is diffeomorphism invariance. So that means that the Lagrangian, to be local, it has to be built out of the Riemann tensor and covariant derivatives of the Riemann tensor in scalar contraction. So very schematically, the generic form that you get is local operators built out of some overall powers of Riemann, some overall powers of covariant derivatives. This schematic form, do not be confused by the derivatives, do not all have to sit at the front. I simply mean a local operator with this number of powers of derivatives and this number of power Riemann tensor, but they can come in various contractions. For example, Riemann to the 50, and then box to the 20, and then Riemann to the 100, or all sorts of local operators, everything local operators like that. So that's general relativity as an effective field theory, with no other degrees of freedom. Of course, these terms get smaller and smaller as you go on. If the curvature is small relative to whatever the cutoff scale is, so for example, maybe the Planck scale, the derivatives are small relative to the Planck scale, these terms get smaller and smaller, and that's why effective field theories, despite containing an infinite number of operators, are nevertheless useful, because in practice you only need to truncate them at a given order in the expansion, and you compute things to that order. The leading terms, for example, are the curvature squared terms, and then you have curvature cubed and curvature squared box terms. I'll get to later. That was pure GR. Similarly, if you have light fields, they may be the standard model. It may be inflaton, whatever it is, you just repeat that logic. So now my light fields includes the metric and some other light fields, matter, standard model fields, whatever. And so then I just write down, I have more combinations of local operators that I can write down, which schematically take that form. So you may ask already, it's an interesting question, do these operators that you do expect to get basically in any UV completion, do they affect low energy observables? So for example, do they affect the propagation of gravitational waves? Well, the answer is technically yes, but in practical terms, those effects are very small, but nevertheless, it's interesting to think about them. So as I mentioned earlier, there's two types of effects you get from heavy physics. There's tree level effects and there's loop level effects, depending what you're integrating out. Now, specifically to modify gravitational waves, because gravity are spin 2 degrees of freedom, to essentially get any modification to propagation for spin 2 stuff, at tree level, you have to be integrating out fields which also are spin 2 or higher. So integrating out scalars and vectors, for example, will not affect propagation of gravitational waves. The same is not true at loop level, and that's because within the loop, essentially when you cut a loop within the partial wave expansion of a contribution from a loop, you have all spins. Loops contain effectively states of intermediate states of all spins. So you can get corrections to the gravitational part, but how they come about depends slightly on context. So it's interesting already just to think about these leading two effects, which are very often considered in the literature precisely because they are the leading two. So in 4 dimensions, the Gauss-Bonnet term is irrelevant because it's a total derivative. It's irrelevant for local physics in any way, but you have the Ricci scalar squared and the Wahl tensor squared, as particular pieces. Now, the Ricci scalar square doesn't affect gravitational waves because it's a scalar, but the Val tensor does because it really encodes them. Now, it's well known that these particular terms can be removed with field redefinitions, but doing so is not an innocent process. When you perform a field redefinition of the metric to remove those terms, you modify the coupling to matter. And so you're actually just moving a problem about. And so it does depend, depending on what your original coupling to matter was, there is still content in these terms, even though they technically may be regarded as redundant operators. You can remove them with a field redefinition. That's an important point. So once you couple to matter, you can't arbitrarily field redefine the metric away. And so it does make a difference. Precisely what that field redefinition is looks like this. So if you wrote Lagrangian, if I reorganize it in this particular combination, so I write the Val squared out as a combination of Gauss-Bonnet, Ricci tensor squared and Ricci scalar squared, it comes out in these particular combinations. Again, the Gauss-Bonnet term is basically irrelevant. Both of these terms can be removed with a field redefinition. At leading order, that field redefinition looks like this. It's not particularly illuminating, but it is what it is. And after that field redefinition, what happens is you make the gravity sector conventional. So it's now just Einstein-Hilbert plus Gauss-Bonnet. Again, Gauss-Bonnet is irrelevant, but you make the matter sector unconventional. So you generate non-trivial interactions in the matter sector. And that's why things are still corrected by that. So for example, it's a cute exercise to see, how is the propagation of gravitational waves corrected on FRW, which is relatively simple to do. You just write the metric for FRW in this form, look at perturbations around it. You get some equation that after a little bit of rearranging looks like this. So it looks not dissimilar to your usual equation on a curved space. I've written it in conformal coordinates. So this is basically box. The scale factor for FRW is sitting out front. There's a sort of effective mass term. You get effective friction contribution. But also, in particular, you get a slight modification for the speed of propagation, albeit one which is suppressed by the cutoff of the effective theory. So in this case, I'll put it in at, essentially it's in Planck squared suppressed. So you do get a modification. If you do that in the field redefined picture, it's quite interesting to do. There, gravity is, if you like, conventional, but the matter's non-conventional. So what happens there is that gravitational waves in that sector are always luminal to that order, because the Einstein gravity is basically Einstein gravity up to the Gauss-Bonnet term. But you modify interactions in the matter sector, modify the speed of fluctuations. And the consequence of this is what happens is when under the process of performing a field redefinition, the ratio of the speeds of the gravity waves to matter is invariant. So in one picture, you can have, say, in this Einstein frame picture, the gravity waves are luminal, but say matter is subluminal. In the other picture, it looks like gravity waves are superluminal and the matter's luminal. And you shift that around. And this is a sort of an interesting lesson, because you realize that, of course, you can do field redefinitions to remove terms, but it changes the interpretation of things. Although it doesn't change the overall causal structure. So if something's faster than something else, that sort of remains invariant. That was already just the R squared terms. Even if you set those to 0, which you can do because they're not, they're sort of always ambiguous, because they come in, say, from loop calculations, they're logarithmically divergent. So their overall coefficient has to be fixed in the UV. So you can always tune it that they go to 0. But if you do that, then you move up to the R cubed terms, and they are just generated from loops from matter, and they're finite corrections, finite calculable corrections that you compute in effective field theory. They depend on the spin of the particles you integrate, and so on and so on. And whilst many of those contributions can be removed further with field redefinitions, there are some that can't, because they're built out of the Riemann tensor. So essentially everything with Ricci tensor and Ricci scalar can be removed with a field redefinition, because at leading order Einstein equations fix the Ricci tensor, but Riemann tensor it doesn't fix. So any local operator which is built out of Riemann will, at least this vile part, be unremovable with the field redefinition, so it will have content. And you do get those from loop calculations, and you can compute them. So all this is calculable to some extent, and well understood. And so it's, of course, it's very interesting to ask, well, so what are the phenomenological implications of this? And so we have, as I say, we have many examples where we do get such terms, for say, from alpha prime corrections in string theory, Kaluza-Klein corrections from integrating out Kaluza-Klein modes because they're spin 2 states. Brain world models, we get exactly these kinds of things. Unfortunately, unless you're looking at early universe cosmology where the curvature gets very large, for realistic, say, for example, black hole physics or astrophysics or solar system scale physics, all these terms are typically very small because the curvatures are very low relative to UV scales, typical UV scales we expect. So people do play the game of making, say, one or more of these operators larger than the others, but in practice, that's never really justified. If you make any one of these operators large, ultimately for the effective theory to be consistent and to respect various properties that it needs to respect, for example, positivity bounds, which I mentioned later, then in fact, they all basically have to end up being the same order. In fact, there's very precise constraints on the relative ratio, on the relative ratios of consecutive coefficients in an effective field theory expansion, which prevents you from making any one of these operators particularly large. Now, the problem then is that in terms of phenomenology, in order for the gravitational effects from these terms to be interesting, essentially the scale lambda has to be made so low that you usually, those effects are usually ruled out by other means. So that brings us to IR modifications, which in a sense is where most of the interest has been in terms of extending, going beyond general relativity, largely because it's where the most observable effects are possible. And here the motivation has largely been cosmological, principally because of the cosmological constant, the fact that the universe is accelerating. So this may be taken as an argument that we don't understand physics at large distances. Now, the difference here is that in the UV case, of course, at low energies, it's always the Einstein-Hilbert term plus the cosmological constant that dominates. That's clear just because it's the lowest number of derivative pieces. But if we want to add new physics in the IR at cosmological scales, then we have to do something different. And so we have to break essentially that fact that general relativity is always that unique answer for the leading term. And one way we often phrase this is that, well, general relativity is the unique theory of describing a Lorentz invariant massless spin 2 field as being the dominant carrier of the gravitational force. That's one way we know that we can derive general relativity, including its interactions, just by the requirement that the principal degree of freedom propagating the gravitational force is a massless spin 2 particle. So that really just comes from locality, Lorentz invariance, masslessness, and the assumption that you just have a single spin 2 degree of freedom, that's all. So if you want to go beyond that, it's natural to give up one of these assumptions. So there are people that think about giving up locality, but that's quite a dangerous thing to do for obvious reasons. You may give up Lorentz invariance, and there are many examples, for example, Hajava-Lifshitz of theories which are not Lorentz invariants, Einstein ether theories that are not Lorentz invariant at a fundamental level. But beyond that, most of the ideas then imagine essentially just you giving up the assumption of a single spin 2. So there may be additional states, which, for example, may be spin 0, such as Brown-Sticky theory. Or more seriously, you may give up the masslessness assumption of the graviton. So as I said, the main two ideas that people have thought about, if you forget about breaking locality and Lorentz invariance for a second, is introducing new propagating degrees of freedom that may themselves exchange gravitational forces. That means force between the stress energy. Principally the trace of the stress energy in the case of extra spin 0 particles, or it may be the full stress energy if you have extra spin 2 particles. for example, those that arise in Kaluza-Klein theory. Other approaches that people have thought about in the last 15 years are in a sense more radical, where you imagine that the graviton itself may not be massless, it may be massive, either in a very hard sense, where you have a pole in the propagator for the graviton which has a mass, or in a soft sense, where the graviton essentially is a resonant unstable state, which has spin 2, but ultimately it decays away. And there are examples of those theories. So the original soft theory of massive gravity is the famous DGP-Dvali-Gavadadze-Parati model, which was a brane-world model. There are generalizations of that, such as cascading gravity and so on, and warped massive gravity. And then the hard massive case is massive, what's normally just now called massive gravity, which I'll talk a little bit about later. So these are genuinely alternative theories of gravity, which are more fundamentally change things even in the infrared, and they were introduced precisely to do that. And nowadays, particularly in the cosmology community, people talk about all sorts of things, chameleons, symmetrons, ghost condensates, generalized Galileans, beyond Hundensky, dust theories, all sorts of things going on, which are motivated by these kinds of ideas. Now, many of these models that people think about are in a sense non-standard from effective field theory point of view, in that they may rely on non-renormalizable operators, irrelevant operators, being larger than you would have expected under ordinary circumstances. So naively, you think I must be going outside of the regime of validity of the effective theory. But there are sort of controllable cases where we know that that's not necessarily the case. And probably the best example is, the best examples are when you have some symmetry protecting you that controls the structure of the effective theory that allows certain nonlinear terms to be large without undermining the entire structure of the effective theory. The most well-known example is the DBI model. So if you just look at the DBI model, which its UV completion is basically, it's just a probe brane in an extra dimension. So it's basically the action is just the action, the equivalent of the Nambu-Goto action for a brane living in higher dimensions. From a 4D point of view, the position of the brane in that fifth dimension, if we just imagine there's one extra dimension, looks like a scalar field. It's the position of that brane. And the action has this square root form just because it's a relativistic brane. So it's like square root of 1 minus v squared over c squared is the action for a point particle. This is the brane equivalent of that. Now, because this effective theory has an interpretation as a brane embedded in an extra dimension, it secretly carries in 4 dimensions a nonlinear remnant of that 5-dimensional symmetry, 5-dimensional translation symmetry, which is this DBI symmetry here. And it's a nonlinear symmetry, it's nonlinear realized. Phi shifts by phi, you shift by a constant, that's obviously invariant, but you can also shift it by something that goes like x plus phi d phi. So it's very nonlinear. Nevertheless, you can show that this Lagrangian shifts by a total derivative and the action is invariant, so it's a genuine symmetry. Now that symmetry protects this form of the square root against quantum corrections and allows you to imagine a situation where the velocity of the brane in the extra dimension is of order 1, so it's relativistic, so this thing is order this, without the effective theory going out of control. And there's a couple of ways to see why that's going on. The one way to think about that is that the velocity can be of order lambda 4 in these natural units, but as long as the derivatives of that velocity are small. So as long as the acceleration is suppressed, then the effective theory doesn't go out of control. Another way of seeing it is that the fluctuations of the inflaton around the background can be, so I could call it inflaton because it's been used in the example of inflation. The fluctuations of the DBI field themselves have an effective theory that doesn't go out of control. So this plays a crucial role, for example, in DBI inflation models. Another example, which is closely related, and I'll come back to again, is the so-called Galileon. In that case, this was originally discovered in the context of the DGP model as a particular limit, a decoupling limit to the DGP model. In that context, there's also a nonlinearly realized symmetry where the action is invariant under shifting the field by constant plus v mu x mu. And in that situation, we can imagine a scenario where GD phi is order lambda cubed, which naively the effective theory goes out of control, but in practice it doesn't, as long as derivatives of that are suppressed. Slightly more optimistically, we generally restructure these theories as effective theories for the fluctuations, which I'll get to later what that means. And then we can imagine situations where, in fact, this expression dd phi over lambda cubed, which is the Galilean invariant object, sorry, that's supposed to be much bigger than 1, not less than 1, can even be much bigger than 1 without the effective theory completely losing control. Okay. So that brings me to an important point about specific types of effective field theories that, in fact, differ. Most of the ones in the IR modifications actually rely somehow on the notion of broken symmetries at some play, in particular, for it to be a theory of gravity, broken space-time symmetries. And those are important examples, and I'll focus on those. But just to remind you what I mean by that, let me sort of forget about gravity for a second and just think about gauge theories and what that means. So you're all familiar with the notion that in the standard model, we have gauge fields for which there is a gauge symmetry, a local symmetry. But via the Higgs mechanism, that local symmetry is broken by the Higgs field getting a VEV, which picks out a particular preferred direction, if you like, in the gauge field space. And that's what gives mass to bosons. So when you break the gauge, spontaneously break the gauge symmetry, the bosons carrying the force effectively become massive. Now, there's a useful result, which I'll rely on, which is so-called Goldstein equivalence theorem, is that in a particular limit, in a high energy limit, the scattering amplitude for the additional longitudinal modes that arise in the massive bosons, the massive spin 1 states. So remember, a massive spin 1 state has 3 degrees of freedom, a massless one has 2. So there's an extra state, that's the longitudinal mode that's normally forbidden in the massless case. The scattering amplitude for those additional states are dominated by so-called Goldstein or Stuckelberg effective theory, a particular effective theory that I'll define in a particular decoupling limit. Okay, so just to give you a toy example of that, because I'm going to use that idea, let's think about the Abelian Higgs model. So this is basically the simplest Higgs model. So imagine that we've got a complex scalar field, phi, that transforms under a U1 and Abelian gauge symmetry just by a phase with some charge Q, and chi is the gauge parameter. And you all know how to do this. You're supposed to introduce a covariant derivative for that field so that the covariant derivative transforms the same way. And then in defining a covariant derivative, you introduce a gauge field, which shifts in that particular way so that the covariant derivative has that transformation. Right? That's how you introduce to gauge theories. Now, when you Higgs that theory, when you break the symmetry, what's going on effectively is you're giving a VEV to that Higgs field. So it picks up a non-zero vacuum expectation value, I've just called V here. But still, because it's a complex field, it still has two parts to it. And you can split those parts up into the phase part and then the magnitude, if you want. Now, the Higgs boson is essentially the fluctuations in the magnitude around the VEV. And the so-called Goldstein, or more precisely Stuckelberg field in the case of a local symmetry, is the phase of that. It is that degree of freedom which essentially shifts linearly under the gauge symmetry. So if I do a gauge transformation, which is exponential for phi, for pi, it's just linear. So that's the so-called Goldstein mode in the global limit, or in the local theory, it's the Stuckelberg mode. Now, if you make the Higgs very massive and you integrate it out and you go to the low energy effective theory below the Higgs mass, then what you get is an effective theory just for the Goldstein mode, the Stuckelberg mode, pi. Actually, the quickest way to derive that is, in fact, to first go to unitary gauge, where you fix pi is equal to 0, so that the field phi doesn't even have a phase anymore. And then you integrate out rho, And when you do that, all you've got left is A. But A now, because I've fixed a gauge, doesn't have to come in a gauge invariant combination. So when you integrate out, what happens in the broken phase is you'll generate a mass term. You know you had to, because your bosons are massive in the broken phase. But you'll also have interactions which are not gauge invariant. So you get things like this. So this is the so-called Proctor theory, and that's its interactions. But it's just the low energy theory below the Higgs mass that you get when you integrate out the Higgs mass. What is the effective theory for the remaining degrees of freedom? Now you can reverse that procedure through the so-called Stuckelberg procedure, where you go up again. So from unitary gauge, you can then go up again, and you reintroduce the Stuckelberg-Goldstein mode by performing a gauge transformation of A mu, and then making the gauge parameter itself now function about a field. So you promote the gauge parameter to a field. This is the trick that Stuckelberg did to write the Proctor action in a gauge invariant way. Now I've done this in a very specific way. I've put a 1 over m there. Why did I put over 1 over m? So that the pi here is canonically normalized. So that comes about because if I look at the quadratic term in the action, there's an m squared, you know, before I do this, it's got m squared, mu squared. So after I do that, I want to put a 1 over m here and a 1 over m there so that the m squared cancels and I get a conventional canonically normalized kinetic term for the scalar. So that's determines that normalization. Then the interactions, I have to do the same thing because I've used up that freedom. So this Stuckelberg action is now gauge invariant again. So we did something slightly weird, but the reason we do this is because it's we understand how it generalizes well in other cases. We fix the gauge and then we reintroduce the gauge freedom. And the new action is now obviously gauge invariant again. If I shift a mu plus 2 mu chi, I shift pi goes to pi plus m chi, then this combination is left invariant, and so the action is gauge invariant. And it allows me to count degrees of freedom from the master's point of view. So now, because I've got a gauge theory, a mu I expect to have 2 degrees of freedom because it's a gauge invariant U1. Pi is a scalar, that should be another degree of freedom. 2 plus 1 is 3. So that's the correct number of degrees of freedom I should have for a massive spin 1 particle. So why this trick is useful, it looks perverse to go through it, but why this trick is useful is because now we can take this so-called decoupling or scaling limit, or the goal that focuses in on the so-called Goldstein low energy effective theory, which correctly reproduces the scattering amplitudes in a particular high energy limit. So the point is that at high energies, when energy is high relative to the mass scale, then we can approximate this action by sending m to 0. So if energy is high relative to m, you think, well, you could just set m to 0. But I can't arbitrarily set m to 0, because if I do, because of all these 1 over m's sitting everywhere because of canonical normalization, the interactions will go to infinity. So I have to take a precisely defined scaling limit where I send m to 0, but send other stuff to 0 in such a way that the interaction remains finite in that limit. It doesn't go to 0, doesn't go to infinity, it remains finite. So for example, if this was the only thing I had, what I would do is I would send little m to 0 and little lambda to 0, lambda being the coefficient in front of the a to the 4 term, keeping this scale capital lambda, which is m over little lambda to the quarter, fixed. When I take that limit, because m is going to 0, these a mute pieces are irrelevant relative to this, and I get just this effective theory for the Goldstein mode, now decoupled from a massless spin 1 sector. So this is what we would call the helicity 1 particle, helicity 1 field. This is the helicity 0 of the massive spin 1 particle. And what you see is in that limit, the dominant interactions, in fact, the only interaction limit for this example, although it's a very similar example, the only interactions are the interactions in the helicity 0 mode, and they are dominant. They are the dominant interactions. Now, this is a generic feature. When you have a symmetry that's broken, then local symmetry that's broken, the dominant interactions at high energy in the broken phase, it's really an intermediate scale, so we still have to be able to trust this effective theory, but the dominant interactions at high energy are determined by the interactions of the Goldstein or Stuckelberg fields associated with the symmetry breaking. That's the essence of the Goldstein equivalence theorem. So after that sort of sideline, let's get back to gravity. So this concept has been used copiously in the gravitational community specifically for cosmology and for examples, where you now apply it in a context where we're not breaking, say, U1 gauge symmetry or the SU2 symmetry, but we're breaking the gravitational symmetries. So why would we do that? So in gravity, obviously the global symmetry, if we usually think about the global symmetry, if the cosmological constant is 0, is Poincare symmetry. So the local symmetry is diffeomorphism invariance. But in some sense, these symmetries are always broken by matter, right? When you yourself break translation invariance because you are at a particular point, and so as soon as you are introduced into the system, as soon as a body is introduced to the system, then I can start talking about the distances to that body, and so you break translation invariance. In the context of cosmology, time translation invariance is broken, spontaneously broken. Time diffs is broken. Because the universe is filled with a homogeneous fluid, be it matter, radiation, inflation, whatever it is, it's your epoch, but you're filled with a homogeneous fluid. The fluid looks the same in every space direction, but it doesn't look the same in time direction. So it breaks the time translation symmetry. Similarly, if you talk about, say, a black hole in a scalar tensor theory, a hairy black hole, then that may have some radial profile for the scalar fields, and that will break radial diffeomorphism symmetry. So in some sense, matter does break symmetry in a spontaneous way, and you can use that concept to reorganize your effective theory appropriately. So for example, in the context of inflation or even dark energy, this has been done now, used extensively, but the idea is the same. You follow the Stuckerberg procedure. So we first write down the theory in unitary gauge. This assumes we don't necessarily know what the Higgs theory is. We don't necessarily know how the broken symmetry theory is built into some bigger UV theory. We just know that there's a symmetry that's broken, so it may be time translations. And then you just write down the unitary gauge effective theory, and then you follow the logic of effective field theory. You write down every local operator consistent with the symmetries that you have in your problem, okay? But if you've broken time translation symmetry, or you've broken time diffeomorphism symmetry, I should really say, then you don't write down operators you don't need to write down operators that respect time diffs alone. You can write down operators that are not invariant under time diffeomorphisms. You only need them to respect space diffeomorphisms. So in other words, you build your action out of the three curvature, the curvature of space constant time slices, and the extrinsic curvature on that. These are objects which are invariant or naturally tensors under spatial diffeomorphisms, but not under space-time diffeomorphisms. And then you write down all sorts of things, and because you've broken time diffs, you can write arbitrary functions of time in the unitary gauge action. So you have arbitrary functions of time here and so on. Certain of these functions are fixed in terms of the background expansion. And similarly, you can introduce the 0,0 component of the metric. That is invariant under space diffs, the upstairs G00 was a scalar under space diffs, I should say. And so you can write down arbitrary functions of that. And so you restructure your effective theory in that particular way. And then you Stuckerberg. So the Stuckerberg is what you do. You do a gauge transformation, and you promote the gauge parameter to a field. So in this case, what was broken was time diffeomorphism symmetry. So I undo that. I do a time diff. T goes to t plus a function of x and t, and I promote that parameter to a field. And then then you take a decoupling limit where you focus on certain interactions. Roughly speaking, there's usually a limit in which the dynamics of the Stuckerberg field decouples from the gravity sector, and your dominant interactions are given by these scalars. So it looks specifically like this. And so this is used in the effective theory of inflation, but also in dark energy effective field theory. So where you have quintessence-like field, another light field that acts at cosmological scales that may propagate with forces, which has potentially largish interactions like this. This is a cartoon for the full thing. There's many other interactions you can write down. but it's just to get the general idea. So this is how the concept of effective field theory is in broken states in constructing different extensions to just pure GR and a cosmological constant are written down. Another example, which is perhaps more relevant to this workshop, is that the same ideas have been used for example, for black hole spacetimes. So in this picture, let's imagine you've got a black hole, zeroth order, let's say it's non-rotating, so it's spherically symmetric. If you're in some theory which is not general relativity, then there can be scalar, possibly scalar hair in that theory, depending on precisely what the theory is. So there may be some non-trivial profile for the scalar around the black hole in that particular theory. And in that case, then, and that profile itself is breaking radial diffs in that context. And so you can play a similar game where you can first go down to unitary gauge, in which you try to write down an action which is not invariant under full diffeomorphisms, but you give up radial diffs completely. And that allows you to put arbitrary functions of the radial coordinate out in the effective action. But otherwise, you try and write down operators which are covariant under the remaining non-radial symmetries. And then you Stuckelberg back the radial diffeomorphisms. So the same trick, you write R is R plus pi is the Stuckelberg field. And then in a particular limit, you can take a Goldstein limit of that. And that is, the idea is, again, in a regime of energy scales, that is supposed to represent the dominant interactions in the original system. So it's often more convenient, it's often easier to work with the Goldstone-Stuckelberg low energy effective theory than the full theory you're looking at, because it captures the dominant dynamics of the system. So for example, this particular idea is used in this particular paper. However, my favorite example, to be slightly biased, is where you go all the way and you break all the diffeomorphisms. And those theories are called massive gravity, because in that context, you don't have any diffeomorphism symmetry anymore. So then you completely given everything. Basically, what you're doing is you're giving the bosons a mass in that context. So in that situation, then the symmetry that you're breaking is diffeomorphism invariance. In a massive gravity theory, the way you do that then is you reintroduce back that nonlinear diffeomorphism invariance in a particular way. So what you have to have then is some equivalent of a Higgs VEV for some Higgs field. We don't have a Higgs mechanism for massive gravity, but we can write down the effective theory in the Stuckelberg picture. The difference with respect to the normal Higgs mechanism is the VEV for the Higgs field is essentially itself a spin-2 object. So you can think of there being some fixed reference metric, which itself is like a VEV for some spin-2 object. And then when you Stuckelberg back in the broken symmetry, you do that by basically taking that 2 tensor, which is a fixed one, and then performing an arbitrary coordinate transformation, a diffeomorphism on that 2 tensor. And you promote the field in that diffeomorphism itself to a dynamical field by the Stuckelberg trick. And it's very similar to before, that field decomposes out. To be canonically normalized, you need 1/m's in front. But in this case, it's slightly more subtle than the spin 1 case. The field splits up into helicity 1 modes with 1/m in front, and then helicity 0 mode with a 1/m squared in front. Actually, they come together with an M Planck as well. So the scale that sits in front of the helicity 0 mode is 1/m squared M Planck. So it sandwiches into this scale, this we call lambda 3. And the diff symmetry is a nonlinear symmetry. When you do that when you compute that diffeomorphism version of the reference metric, and you take the decoupling limit, so you try to focus in on those leading interactions in the decoupling limit, then the reference metric in that limit, so the diffeomorphism version of that, becomes something that takes the form of a complete square in terms of this helicity 0 combination. And so if you take the square root of that combination, then it gives an object which is linear in the helicity 0 mode. So pi here, which is the Stuckelberg field, one of the Stuckelberg fields for the mass of spin 2, is literally the Listy zero mode. When I write the 5 degrees of freedom of a mass of spin 2 into 2 plus 2 plus 1, 2 Helicity 2, 2 Helicity 1, 1 Helicity 0, pi is that Helicity 0 mode. And it shows up exactly in this square root combination. Now, it's for that reason that should say about that Helicity 0 mode is it comes automatically in this combination where it has 2 derivatives on it. So it automatically comes out with this Galilean symmetry, because if I shift pi, it goes to pi plus a constant plus v mu x mu, this particular combination is invariant. And so you get in the decoupling limit of a massive spin 2 theory, you get automatically a Galilean. And in fact, by knowing the precise structure of the allowed Galilean operators, or more precisely how Galileans are allowed to couple to master spin 2 fields, you're able to work out what the complete structure of a massive gravity theory with the highest possible cutoff is. Ghost free, it was sometimes called ghost free massive gravity theory, which only propagates 5 degrees of freedom. And basically you build it out of this square root combination, this object which looks like dd pi, picks up the Galilean combination in the so-called decoupling limit. And that fixes the nonlinear interactions. And we now know this to be the unique theory of massive spin 2, interacting massive spin 2 field, where the cutoff is the highest possible scale you can have. Now, massive gravity itself should be viewed as an effective theory. The new feature relative to the old one is that, well, new feature relative to, say, the UV modifications, is that what automatically happens when you try to do IR modifications of gravity is you want to change physics at cosmological scales, but it's also gravitational physics. And in the process, what you generate is intermediate scales. In this case, it's this lambda 3 scale, which is intermediate between the graviton mass scale and the Planck scale. And that scale, that intermediate scale, ends up being the cutoff for this particular effective theory. So at that scale is where, you know, perturbative unitarity is broken, things go a little bit crazy in terms of calculations. But it's also then, when we view massive gravity's effective theory, we should view it as a theory with that cutoff, in which case, in addition to those allowed interactions I've written down, you should then write down all the infinite number of operators that you should be allowed to have in a theory, in an effective theory, which would be local combinations built out of, again, the Riemann tensor suppressed by the cutoff, which now is not the Planck scale, it's this lambda 3 scale. And this combination K and covariant derivatives of that particular combination. So it determines the structure of the massive gravity as an effective theory. So as I mentioned already, a generic feature of these IR modifications versus the UV ones is new physics at an intermediate scale, something that sits between the Hubble scale, which is where you tend to, you want to modify things at Hubble scale today to do something, say, about solve the cosmological constant problem or find an alternative to dark energy. But it comes in at intermediate between that scale and the Planck scale. Okay, so I think, just Claudia, I think I've got half an hour left, is that right?
That's correct, yeah.
Yeah, okay, so I think that's about right. So, I mean, I could have a break, but at the same time, I know I'm always a little bit tight for time. So what do you think?
I mean, maybe we can leave people, it's what, 56 now? We can leave people until o'clock.
Yeah, okay, let's have a 4-minute break then.
So people can drink something or whatever they need to.
Okay.
So let's reconvene at o'clock.
Create any closed time-like curves at low energies. There should be no, perhaps you demand that the theory has no caustics or so on, but low energy consistency questions. Now, the problem with the low energy consistency questions, indeed even causality in the gravitational theory, is that they are sensitive to field redefinitions. And so we've already seen, I've used the example, in certain cases you can perform field redefinitions of the metric, which actually change the effective speed of propagation. Gravitational waves may be luminal in one frame, subluminal, superluminal in another frame. Which is the right one? Which metric am I supposed to use to determine causality? It's dependent on fields. And so it's very, very difficult to address, take that into account. It's also the case that, whether or not your particular effective theory is numerically stable to solving it, can be sensitive to gauge issues and field dependent issues and so on. So it's better to have a sort of more higher minded perspective on what is allowed and not. So one way to do that, to get around that, is to focus on something that isn't dependent on field redefinitions, and that is the S matrix. So the S matrix is famously, as I already mentioned, invariant under local field redefinitions. And therefore, it somehow encapsulates the respectability of effective theory, say, for example, under causality, should be built into that. There's a couple of ways that people have thought about that. So one way is to think about so-called demanding causality by the absence of any kind of asymptotic superluminality. So what this is actually really an old idea. It's what it is basically if you compute the scattering time delay in a scattering experiment. So a scattering time delay is just the rate of change of the scattering phase shift with respect to the energy. So you can compute this, for example, for each partial wave in a 2-2 scattering experiment. Causality is usually required that this scattering time delay is positive, so that it's not a time advance, or at least it's bigger than a certain, the amount by which it's negative is somehow constrained in a particular way. So that's one way people look at effective theories, constrain them by demanding causality from positivity of the scattering time delay. There's another idea that is quite popular at the moment, which comes from another aspect of the scattering matrix, which is how causality is built into the scattering matrix, which is that it is an analytic function of its Mandelstam variance. So if you commute scattering on Minkowski space, then you know that the scattering amplitude can be written in terms of Lorentz invariant combinations, a so-caued Mandelstam invariance. And it's supposed to be that the scattering amplitude is an analytic function of that, and analyticity, roughly speaking, encodes causality in a particular theory. In certain cases, that's defined in a precise way. So for a fixed momenta transfer T, you can show that the scattering amplitude has to be an analytic function of complex S because of causality, at least in a theory which satisfies certain requirements. Now, these assumptions lead to the so-called positivity bounds or positivity constraints, which again is an old idea, but is being used significantly at the moment in constraining the form of low-energy effective theories. And this uses the old 1960s S-matrix law, which is that the S-matrix as an object, so if we just think about the 2-2 scattering amplitude, but the S-matrix should obviously respect unitarity. Usually you require it to be local in a precise way. So that means that the scattering amplitude doesn't grow faster than usually the old assumption is it shouldn't grow faster than a polynomial in any direction in the complex momenta space. Causality, as I've already mentioned, is encoded in analyticity, Lorentz invariance, and you also have crossing symmetry. And in the old days, people assumed the presence of a mass gap, although nowadays we're slightly more open about that particular assumption. Now, why this is useful is because from these basic assumptions, the analyticity in particular, you can write down a dispersion relation for the scattering amplitude. So here is a scattering amplitude that follows from those assumptions as a function of the two Mandelstam invariants, S and T. So S is the center of mass energy, T is the momenta transfer. And that scattering amplitude is supposed to be an analytic function of S at fixed T up to poles, which correspond from just, the direct tree-level exchange of a particle of a given mass, and branch cuts, which come from loop effects in general. Although within the branch cut may be other poles, but principally its branch cuts come from the loops. And because it comes from loops, it starts at 4m squared and goes up to infinity. And there's a crossing symmetric branch cut which goes to the left. So you have a right-hand branch cut and a left-hand branch cut, a pole, physical pole at m squared. And then again, because of crossing symmetry, which is where I can then change s and u. So it's this process. If I take a plus b goes to c plus d and I switch b and d, then that switches s and u around. And so the amplitude is supposed to be invariant under that. It's a scalar amplitude anyway. So you then, that's the right-hand branch cut and that's the left-hand branch cut. So you can use Cauchy's theorem to write down dispersion relation for the scattering amplitude. And why that's useful is this imaginary part that comes in the dispersion relation, which is the discontinuity across the branch cut. It has to be a positive function, both in the forward limit when t equals 0, but also for small positive t. So for unphysical momentum transfer, but positive t, it has to be a positive function. And that just comes from the partial wave expansion. The imaginary part of every partial wave is positive by unitarity. And in imaginary part of the amplitude as a function of t, the partial waves come in positively for small positive t. And so these are positive functions, hence the positivity bound. So for example, one thing you can show, if you take the amplitude and you subtract out the pole contribution, so remove the poles, which I can always do because I can calculate those in the low energy theory. If I differentiate then the resulting amplitude, in other words, I do a Taylor expansion and I look at the coefficients in that Taylor expansion. All the coefficients in that Taylor expansion are given by integrals over positive quantities, and they're therefore positive. So in other words, the Taylor expansion of the scattering amplitude for fixed small positive t has positive coefficients all the way up. And indeed, more than just the positive, you can also derive all sorts of non-trivial relations amongst them, which people are playing around with at the moment. Now, one direct consequence of that is it does put constraints on effective theories. For example, the most famous example is these so-called Goldstein-like P of X type theories. So imagine you've just got a Lagrangian, which is just d phi squared plus d phi to the 4. So one of these Goldstein-like effective theories, which respects a shift symmetry. If you compute the scattering amplitude in this theory, it's determined the 2 to scattering amplitude is just proportional to the coefficient c. And so if you subtract out the pole, well, there is no pole in that example, and then differentiate it twice, you get something which at tree level goes like c. At one loop level, you get an extra c squared contribution, demanding that that's positive, enforces that this coefficient c has to be positive. So that's one of these positivity bounds. Now, to see that this correlates with causality, you can show that if you look at fluctuations of the scalar around some given background, the speed of those fluctuations is typically given in this form, in this example, and c has to be positive for that speed to be subluminal. So it seems to be that positivity bounds essentially a way of encoding causality in a given effective theory. And that's not surprising because deriving the positivity bounds, deriving this positivity of all these particular terms in the Taylor expansion comes from using analyticity. So for example, this rules out the so-called anti-DBI effective theories, if you're ever interested in the anti-DBI. So DBI is like a brain moving in one extra space dimension. What happened if you had one extra time dimension and had a brain moving in that? Well, that sounds bad. Well, indeed, it is bad. It's ruled out by these positivity bounds because the Lagrangian for that would have the opposite sign inside the square root. When you expand it out, you would get exactly opposite sign for the d phi to the 4 term, and that would be ruled out by the positivity bound. So it seems to make sense. So this basic idea, once you've got the idea, that's the main thing, that is being applied in all sorts of effective theories at the moment. There's quite a lot of papers coming out. I'll just mention briefly with the application of these to massive spin 2 theories, because that's what's been most interest to me. So there's a couple of interesting results that come from that. So if you naively try to write down, I've already given you this sort of natural so-called lambda 3 massive gravity theories, the ghost free theories. But if you just naively write down in unitary gauge massive gravity theory. So you take Einstein-Hilbert gravity and you just start writing down, because you're in unitary gauge, I can write down things that aren't gauge invariant. So I just write down arbitrary mass terms, arbitrary interactions suppressed by an overall mass scale. When you do that, what you find is that the cutoff scale of that effective theory is actually a very low scale. It's the lambda 5 scale. So up to now, I've been mentioning this lambda 3 scale, which is the cube root of m squared m Planck. There's a much lower scale, which is the lambda 5 scale, where you have 4 powers of m, 1 m Planck, and take the 5th root of that. So that's a scale which is parametrically much closer to the graviton mass scale and further away from the Planck scale. So that's the typical scale that you get when you write down arbitrary interactions. So you can take those classes of theory. I mean, they're okay, actually. They're effective theories with just a very low cutoff. And it's interesting then to apply the positivity bounds directly to them. And it turns out, so what happens is that if you parameterize, say, the effective mass term up to quartic order with some coefficients, and you parameterize the departure of those coefficients from the special tuned values that give the so-called ghost-free massive gravity that we talked about earlier, the lambda 3 theory. So these are the departures from that. What you find is that the positivity bounds, the forward limit positivity bounds, demand that this particular coefficient delta C is 0. By requiring that this quantity is positive, you can show that when you do that for all different polarizations, the only choice is that delta C is 0. And the positivity bands that extend beyond the forward limit also impose that this coefficient is equal to 0. And so together, positivity bounds basically fix the departure from the lambda 3 massive gravity theory to be 0. In other words, they, at least up to quartic order, which is all this argument probes, positivity bounds precisely encode the tunings that you have that promote a lambda 5 massive gravity theory, which is the generic one, where you don't have this special ghost-free structure, up to the so-called lambda 3 massive gravity theory. So those are the two example theories, and it automatically forces that. So that's kind of interesting consequence, just one example consequence of the use of these positivity bounds. And once you're up to the lambda 3 once you're up to the lambda 3 theory, then you can also then just directly apply positivity bounds by looking at scattering for all different polarization states. And there again, you get an interesting result. There's a nice paper by Chung and Raymond in which they showed that for the 2 allowed mass parameters in lambda 3 massive gravity theories, you find that they're essentially almost the entire parameter space is ruled out, apart from a small island, which is allowed, where positivity bounds are consistent. The same idea now is being applied heavily in beyond standard model effective theory, so to put constraints on operators that go beyond the standard model corrections. And if, for example, we've recently looked at extensions to when you have multiple interacting spin-2 fields. So you've got two spin-2 fields, so you have 2 metrics, H and F, and you can put interactions between them. So 2 massive spin-2 fields, put interactions between them. You get very strong, similarly, when you run all the positivity bounds for different polarizations, you get very strong island-like constraints on the allowed region of the different coupling parameters. So this has been a very powerful technique that people are using now, because it really does put strong constraints on the allowed theoretical constraints on the allowed parameter space of effective field theories. Okay, so for my last section, I'm just going to talk about a few observational. I don't have a lot of time, so just talk about a few observational consequences of certain classes of theories, in particular, so the massive gravity type theories, and they come in many different ways. And so, as I say, the IR modifications are more extreme than the UV modifications, because you really change, because you have multiple scales. You have, say, you may change things at cosmological scales, but you have new physics at an intermediate scale. You also have additional states, which can propagate additional fifth forces. So there's many consequences of that. So for example, if you give a graviton a mass, then ultimately you'll get a Yukawa suppression at large distances, which will switch off at the force. And so you can put constraints on whether or not you see that Yukawa suppression. You also change the dispersion relation for gravitational waves, you can put constraints from that. But you also get extra fifth forces that are exchanged by the additional states in the theory. One important example is the dispersion relation already mentioned. Just the fact that if say gravitational waves did indeed have a mass, then it is the case that the lower momenta waves, the longer wavelength waves move slower than the high wavelength ones, and so that ends up squashing the waveform emitted from some binary system collapsing as the frequency goes up. The high wavelength waves going faster, and that squashes up the waveform. And so this is used, for example, to put constraints on the graviton mass from waveform detections. But the main thing I want to focus on in these last few slides then is a key feature that arises in massive gravity, but also arises in Galilean effective theories, Wondensky-like theories, warp massive gravity, DGP, and so on. It's a whole class of theories that rely on the so-called Weinstein screening mechanism. So the key reason you need the screening mechanism is that in a massive gravity theory, a massive spin 2, it has 5 degrees of freedom if it's Rein's invariant. It says 5 degrees of freedom, 2 plus 2 plus 1, you get an extra helicity zero mode. If you compute in a linearized theory, the force between two sources, two stress energies. So for example, you compute the force between the apple and the earth, or the bending of light around the sun. If you do that in a massive theory using the linearized theory, you'll get the wrong answer. You'll get an answer which would be ruled out. And the reason is that in a massive, because of those 5 degrees of freedom, the metric induced by a stress energy is determined by this combination, which is T mu nu minus a third eta mu nu times the trace of T flat space. So it's that particular combination that determines, of the stress energy, determines the strength of the gravitational wave. But in general relativity, of course, it's this minus a half combination that comes in just because of the form of the Einstein equations. And it is never the case that a third is a half, even in the massless limit. So this is the famous V divis E discontinuity. The massless limit of a massive particle, massive spin 2, is not a massless spin 2, because even in the massless limit, 1/3 is not equal to 1/2. Now, what's going on is that in the massive theory, there's an additional helicity zero mode that propagates a force between the trace of the stress energy. Now, if that is allowed to freely propagate that force, it will just be ruled out. It will completely change gravity in the solar system. It changed the bending of light around the sun. Everything will be completely different. Now, the reason that is not the case, as was recognized a long time ago by Weinstein, is that you also have that argument is based entirely on the linear theory. But because of this intermediate low scale interactions, these lambda-3 interactions, well, it's not the way Einstein phrased it, but that's the way we understand now. Because of the nonlinear interactions of this scale, then what happens is that the linearized formula for the fifth force isn't correct anymore, and you have to do it nonlinearly. When you do it correctly nonlinearly, what you find is that there is a region inside the so-called Weinstein region, or Weinstein radius, where the extra fifth force is suppressed by a power law relative to what you would have expected had you trusted the linear theory. So at large distances, the linear theory is correct, but inside the Weinstein radius, our star written here, the force gets suppressed by a power law. But that radius ends up being huge. For example, for the solar system, if you just compute that radius for the sun, it ends up being like 250 parsecs. So it means that the entire solar system is inside this region. So the fifth forces are suppressed, and that's why we're not ruled out by the bending of light from the sun. If you just naively apply that for a pulsar, just from this static suppression, for example, the fifth force is actually suppressed by the order 10 to the minus 15. But that's not the end of the story. Okay, that's the static force suppression. An important question to address in these class of theories is the dynamics. So how, for example, because you have an additional helicity modes, celestia zero modes, you have additional modes of gravitational radiation. So you have, for example, scalar gravitational radiation, because it's being sourced by the trace of the stress energy. So for example, now a binary system, such as a binary pulsar, can emit into that scalar gravitational radiation. This is a generic feature of infrared modified theories where there's a non-trivial coupling. And you need to make sure that that doesn't happen so much that you're not ruled out already, because we know GR works super well. So, so for example, in a binary pulsar system, so let's imagine now we've got a binary pulsar as written here, there ends up being a hierarchy of scales. So as I said, the Weinstein radius is a super big scale typically. So the binary pulsar system is well inside the Weinstein radius. Our bar here is basically the typical distance between the two pulsars. But there's also another scale, which is the frequency scale. So as the system is orbiting, obviously there's a length scale associated with the orbit time, which is 1/omega. So for a typical binary pulsar system, this is the Schwarzschild radius, that's the distance between the pulsars, that's the frequency scale, that's the Weinstein radius. There's a hierarchy of these different scales, they're all different. So to compute, you can do an analytic computation just to get a sense of how this works. So for example, we can do this for a toy model of massive gravity that arises in the DGP, just a cubic Galileon. So that as an effective theory, this looks like this. So in the so-called Goldstein decoupling limit, you have essentially the pi degree of freedom is the Goldstein mode, is a Stuckelberg field, and it's coupled to trace of stress energy, and that's the field which is responsible for this extra fifth force that V dvz would say rules you out. But it doesn't rule you out because of these nonlinear interactions. It doesn't rule you out automatically, I should say. And the way you do this calculation, you can do an analytic calculation for what you expect is that, given, say, two pulsars, the stress energy is like a sum of delta functions which are orbiting each other. Take the sort of average of that, which is just the center of mass. So imagine the pulsars are all sitting at the center, and take the total mass. That basic source will create a profile, a background profile for pi, which will be nonlinear. And it'll be induced to be highly nonlinear because of these nonlinear interactions. So the way you do that is you split pi, the general field, up into the background profile induced by imagining the entire pulsar is located at the origin of coordinates. And then the fluctuations around that, which is where the gravitational wave part will be encoded. So optimistically, if this term is small relative to this, you can solve for this part exactly nonlinearly. And it turns out its equation, basically that you get an exact local equation for the radial derivative of pi in terms of the total mass of the system. You can solve that exactly nonlinearly and compute the radiation perturbatively around that. So this is an analytic approach to do that. And the way this works is that the effective action for the fluctuations gets, when you take this, sorry, the previous, where is it? Going backwards. You take this action, and you plug in that expansion. The effective action for the fluctuations has an effective non-minimal kinetic term, which comes from the dressing of these higher derivative interactions. And this is the way the Weinstein mechanism works. What happens within the Weinstein radius, this effective metric departs significantly from the Minkowski metric. In fact, it becomes huge in value. It basically grows like a power law. Its value becomes large. Now, if you make the coefficient of the kinetic term large, it's equivalent after canonically normalizing to suppressing the coupling constant, because if I do phi goes to 1/√z phi, that makes the effective coupling to matter small. And that's how the fifth forces get suppressed, and how the Weinstein mechanism works, by the effective kinetic term for the fluctuations becoming large. So to compute the radiation in this process, you do the normal thing. You expand in spherical harmonics, time-dependent spherical harmonics, etc. And for example, you can use the effective action approach of Goldberger and Rothstein. So you just solve for the linear fluctuations given the source. The new thing is your propagator, your Feynman propagator or your retarded propagator, depending on which one you're doing. In this approach, it's the Feynman you use, satisfies a non-trivial equation with a non-minimal effective metric. So even though the actual metric is roughly flat, the effective metric for the scalar is non-trivial. So plugging that back in, the effective action, which is quadratic in the stress energy fluctuations, has this modified Feynman propagator sitting inside it. And then using the Goldberger-Rothstein approach, you compute the radiated power from the imaginary part of that effective action, because the imaginary part of the effective action is the thing that's encoding the decay process. And when you compute it, it ends up being given by this nice, elegant formula, which looks like the normal, very similar to what you get in GR, except the moments are given by basically these integrals over the stress energy source with the wave functions that specifically solve the modified wave equation in this effective metric. And that's the key thing. So the Weinstein mechanism still plays a very crucial role because of this effective metric. In fact, that's entirely where it comes in. And so the mode functions that you solve for satisfy this non-minimal equation. And you can infer them more or less approximately using a WKB matching procedure, because you can solve them exactly at large distances, you can solve them exactly at small distances, and the WKB approximation is good enough that it matches you into those two regions, and you can match the two onto each other and get an analytic expression for the power. And the analytic answer basically tells you that you are dominated by quadrupole radiation, even though there is non-zero monopole radiation. There is non-zero monopole because the trace of stress energy is not conserved. There is a relativistic correction to it. But the monopole is still suppressed because it is only a relativistic correction. And it does turn out that analytically, the dominant contribution is the quadrupole. But that quadrupole is still suppressed relative to GR, both by a sort of static Weinstein screening suppression, which comes in at the Weinstein scale, and also, but it does get slightly enhanced by the orbital frequency scale. And just to end, because it's end on a nice picture, we did some numerical simulations of that. So that was an analytic approach. This is just now a numerical simulation of a binary system. So what it really is two Gaussian approximated delta function sources orbiting each other at some fixed frequency. And what you're looking at are the scalar gravitational waves coming out of that, specifically in this cubic Galilean model. And what you see very nicely there is that after the system relaxes, what you see is quadrupole radiation, very nice and clearly as the system is orbiting, coming to the end of that. And when you compute the power in all the different multipoles numerically, you find that it is indeed completely dominated by the quadrupole. That's the red line here. This fuzziness is just the system settling, but after a while, the total power is completely dominated by the quadrupole in a way that's consistent with that analytic estimate. So my final slide, just a summary then. So as I said from the beginning, the AFT methods are well established for UV modifications. But from a phenomenological point of view, they are typically the less interesting because in most realistic cases, the curvature is not large enough to really make those effects particularly significant. So most of the interest in beyond GR theories is really in IR modifications, which have separately been introduced for cosmological reasons to sort of understand dark energy, cosmological constant, etc., etc. And those theories generically are interesting because they have new physics and new scales, not just at the cosmological scale, but at intermediate scales between the cosmological scale, the Hubble scale today, and the Planck scale. Depending on what the theory is, very common is this so-called lambda 3 scale, sometimes it's lambda 2, and so on and so on. And these types of effective theories emerge very often in the context of broken symmetry effective theories. And the various common features emerge, such as you get these approximate global symmetries like shift symmetries, Galilean symmetries, Goldstein-like symmetries. And the decoupling limit is dominant at determining the dynamics of that. And then just at the end there, I didn't put it in my conclusions, but we saw how you could put theoretical constraints on effective theories from positivity bounds. And I gave you some examples observational effects, specifically from the Weinstein mechanism, which is only very poorly understood beyond the static case. For example, one of the things about the nonlinear screening mechanisms is it does not very fit at all into the sort of standard post-Newtonian parameterizations that people utilize for gravitational waves. So I think I'd better end there. Is that right, Claudia?
Yeah, I think you're, yeah. Thank you very much.
My slide.
Okay, thank you very much. I think Thibault has a question.
Yes, maybe I should put the video too. Very good talk, Andrew. I won't ask about Weinstein because you said this is still optimistic to believe it works. But yes. I have problems about lambda 3. Yeah. Lambda 3 is 10 to the 4 kilometers or something like that, no? So you are saying that if we have a massive graviton at the Hubble scale, there is new physics going on at the size of the Earth, and so So we need a UV completion of massive gravity. How do you see doing tests in the solar system if we have quantum?
Yeah, so that's the initial story. So there, what you're doing is you're computing the cutoff based on scattering around Minkowski space. Mm-hmm. But when you're actually in the solar system, you're already deep in the Weinstein region. So then actually the calculation's a little more subtle. So you actually, if you probably remember this from the DGP days, right, is that then the effective cutoff scale gets raised by the Weinstein mechanism. And I think in my slide it had it, the optimistic scale gets raised by this root Z factor in the Weinstein theory. So then it's actually, the length scale is much smaller in that terms. However, you're absolutely right. As a gravitational theory, it's got a relatively low cutoff, and we do, of course, we can probe distances smaller than that. So it's not meant to be a UV complete theory. It's, you know, these things were introduced mainly to describe large distance cosmological scale physics, but clearly something has to go on at smaller distances.
And are there observational situations like intergalactic where there is no Weinstein mechanism and you would see the lambda 3 scale, just for my information? Yes.
Yeah, I'm sure. I mean, you've seen, we had discussions on this before, but I mean, you know, the naive Weinstein argument, of course, is based on, works very well for sort of static situations and situations with a high degree of symmetry. When there's less symmetry, it's not obvious that it works as well. And so it's in those scenarios where it's not perfect. So you know, to some extent, because you have to rely more on numerics in order to say what's going on, because you have less analytic control, we have less, you know, people have done analytic situations where there is a lot less symmetry, and then you see indeed that you can start to see more significant effects. But on average, it does tend to work. It does tend to wash out the effects of the fifth forces.
Okay, thank you.
I mean, there's others that are better asked to, you know, could better answer those questions in regards to, say, structure formation and so on.
Yeah, I think that's a very interesting point. I mean, there's quite a lot to talk about, so it may be a good point to discuss during the discussion before the first talk. If there anyone else, I'd like to ask a quick question before the next lecture. Oops. I know some people may have issues. Yeah, Filippo, you like to?
Yes.
Yeah.
Hi, Andrew. Thanks a lot for the very nice lecture. I have a question concerning the emission of gravitational waves in cubic Galileon. So, if I understand correctly, you split the scalar field into a background part and the perturbation. Yeah. Can you check that higher the qubit terms, for instance, in the perturbation remain small?
Yeah, that's an excellent question. So, I mean, my answer to that is that just do it numerically, see how well you do. So to some extent, that is the check. But you hit on something exactly right. So the cubic, I think, works quite well. When you do the same analytic calculation for the quartic Galileon, completely falls apart. Yes. And it falls apart precisely because obviously when you expand around the background, you still have interactions for the fluctuations. And the interactions for the fluctuations are actually not suppressed enough at the 1/omega scale, which is the scale that you actually generate radiation.
Exactly.
And for that reason, the analytic attempts to do, say, quartic Galilean just fall apart. There is no analytic formula, and you have to rely on numerics. But the cubic one works reasonably well.
I see.
So it's, yeah.
I mean, if I can add something about that, the funny thing is, analytically, it completely falls apart. But if you try to do it numerically in the same way as you do it for the cubic, it seems to remain under control. So there must be addressing going on, which is not obvious from the analytic part, or at least the analytic part is not doing the proper regressing that should be occurring.
Yeah.
Yeah, exactly. Right. Naively, analytically, it's difficult to see that they remain small. That's
right. Yeah. But I think, I mean, we have done numerically, we have done quartic Galilean, and as Claudia says, actually numerically it seems to work out, and you still get basically the same. The phenomenological scaling, the power law scaling of suppression you expect still works out about right.
Okay, thank you.
If there's maybe one quick question before the next lecture. And I should say, if you have trouble raising your hand, just talk.
Okay, I'll stop sharing.